Welcome to SSR Pharma Media, your trusted source for pharma knowledge. Pharmaceutical Inorganic Chemistry MCQ series, your exam power boost. Today we are going to discuss about radiopharmaceuticals. Prepare, practice, succeed. So, under the radiopharmaceuticals, we are going to cover the radiopharmaceuticals. In that, basic of radioactivity, measurement of radioactivity, properties of alpha beta radiation, gamma radiations, half-life of radiopharmaceutic substance, radioisotopes, and safe handling, storage, and disposal of radiopharmaceuticals, regulatory guidelines for safety. In that, applications of radiopharmaceuticals. So these are all the compounds they have given in the syllabus, MRB syllabus, as well as in the subject syllabus. Sodium iodide 131, iodine 131, technetium 1999 M, cobalt 60, phosphorus 32, ferric citrate 59, and finally the last topic, radio opaque medium. So in that the compound is barium sulfate. So these are all the topic under the radiopharmaceuticals we are going to cover. So first is the basic of radioactivity. So what is radioactivity? Radioactivity is the spontaneous disintegration of an unstable atomic nucleus with the emission of radiation to achieve stability. So that is called radioactive substance. So the type of radioactive decay are alpha decay, beta decay, beta in that beta minus, negative, and beta positive, and gamma emissions, and finally electron capture. So in that, so once the substance undergoes the spontaneous disintegrations, so it's of an unstable atomic nucleus, it's emit the radiation. So that emitted radiations are three types: alpha, beta, gamma radiations. So in the properties of alpha, gamma, beta radiations are very important. First is the alpha, gamma, alpha, beta, gamma. So in the nature of this first property is nature. So nature of alpha is H2 plus nucleus, electron in the positron. So there are two particles, electrons or positron, and in gamma, EM electromagnetic radiations. And in charges are plus 2 charges. So both minus charge and plus charges are there in beta particles, and gamma always neutral charge. So that means alpha is a positive charge, beta is a negative charge, and gamma is a neutral charge. So mass number is high in case of alpha, beta is a low, and gamma is a no mass number. So penetration power is very important. This penetration power and ionization power and shielding power. Penetration power of alpha particles very low, so it can cross the even single paper. It can cross the radiations even single paper. And in the beta particles moderate, so it can penetrate into the thickness of some thickness of the papers, like concrete thickness. So such concrete thickness it can penetrate. And gamma is a very high penetrating power, so it can penetrate even the high thickness of the building, like building itself. So it's a high penetrating power. So due to this high penetrating power only, the gamma radiations always used in the for scanning and diagnosis purpose we use. And due to the low penetration power of alpha particles, so it may use for the some treatment purpose. And ionizing power is a very high ionizing power, so that it is used for the treatment of cancer therapy. And beta is a moderate nature, gamma is a very low ionizing power. So because it's a high penetration, it will go from one one side into another side. So that's why it's a low ionizing power. And shielding effect, it can shield by the paper or skin. So it's shielded by the aluminium. So for the aluminium, till the aluminium, it can penetrate. And gamma radius is a concrete and lead. So shielding. So next is we'll move into the questions. So radioactive is the best defined as, so option C, spontaneous disintegration of an unstable nucleus with emission of radiation. So which of the following is not a type of radioactive decay? So option D, photoelectric emission. So remaining and all, it is type of radioactive decay. Which radiation consists of a helium nucleus? He2 plus. So option C, alpha particles. So 2 protons and 2 neutrons. So it's helium nucleus. Which radiation has no mass and no charge? So option C, gamma rays. So gamma rays is a type of electromagnetic radiation with no mass and no charge. The radiation with the highest penetrating power is, so option C, gamma rays is the highest penetrating power but lowest ionizing power. Which radiation has the highest ionizing power? So option C, alpha particles. So alpha particles highest intense ionization power due to higher mass and charge. Which material is most effective for shielding gamma rays? So option D, lead and concrete also. So next is in basics we are going to cover some definitions of the terms. What is isotopes? What is isobar and radioisotopes? So isotopes means atom of the same element having same atomic number. Z is a symbol of atomic number but different mass number. So A is the symbol of mass number due to different numbers of neutron. And as example, hydrogen. Hydrogen is having same atomic number with the same atomic number. So hydrogen, this so down is atomic number. Hydrogen is a protium, deuterium, tritium. So same atomic number but different mass number. So mass number, upper side is mass number 1, 2, 3 is the mass number, but hydrogen is the same atomic number 1. Isobar means atoms of different elements having same mass number but different atomic numbers. So mass number is same 14 and the atomic number is 7 or 6 or 7. And isotopes, radioisotopes, isotopes with unstable nuclei that emit radiation spontaneously to attain stability. So it's iodine 131, technetium 99M, phosphorus 32. So isotope is the same Z. Z means it's the atomic number. Isobar is the same mass number. A means it's a mass number. So radioisotopes means unstable and radioactive. Isotopes are atoms that have the same, option B, atomic number but different mass number. Which of the following pairs represent isobars? So option B, C14 and N14. Isotopes are best defined as isotopes that radioisotopes are best defined as isotopes that, option C, have unstable nuclei and emit radiation spontaneously. Which of the following is a radioisotopes commonly used in nuclear medicine? So option C, technetium 99mm. Technetium 99M. So next is the unit of radioisotopes: becquerel, curie, millicurie, microcurie. So these are the units of isotopes. So curie means is the SI unit of radioactivity, activity of substance in which one nuclear disintegration occurs per second. So 1 becquerel. Curie is the activity of radioactive substance undergoes 3.7 into 10 to the power of 10 disintegration per second. So 3.7 into 10 to the power of 10 becquerel. Millicurie is the 1,000 of curie. So 7.7 into 10 to the power of 7 becquerel. Microcurie is the 1 millionth of curie. So 3.7 into 10 to the power of 4 becquerel. So SI unit of radioactivity defined as 1 nuclear disintegration per second is option B, becquerel. BQ is a symbol. Curie, 1 curie is equivalent to, so option C, 3.7 into 10 to the power of 10 becquerel. Which of the following represents 1000 of a curie? So option B, millionth curie. Which unit represents 1 millionth of a curie? Option D, curie, microcurie. Microcurie. If a radiopharmaceutical has an activity of 3.7 into 10 to the power of 7 becquerel, its activity in curie units is, so option B, 1 millionth curie. So next is the half-life of radioactive substance. So half-life means it's a time required for 50% of radioactive atoms to decay. So formula is T half is equal to 0.693 divided by gamma, where gamma is the decay constant. The importance is determine clinical usefulness, and short T half leads less radiation exposure. Ideal radiopharmaceuticals are short effective half-life, and example technetium 99, T half is 6 hours. And radionuclidic purity is defined as the percentage of total radioactivity present in radiopharmaceuticals that is due to desired radionuclide only, with no contamination from other radionuclide. The half-life of radioactive substance is defined as option C, time required for 50% of radioactive atoms to decay. The half-life of a radionuclide is related to its decay constant by, so option B, T half is equal to 0.693 divided by lambda. Radionuclidic purity of radiopharmaceuticals refers to option C, the percentage of total radioactivity due to the desired radionuclide only, without contamination. So next is the measurement of radioactivity. The radioactivity is detected and measured based on the ionization and excitation produced by radiation in matter. So according to that, there are several methods are there. First is a Haiger-Muller counter method, ionization chamber method, scintillation counter method, solid state detector, dose calibrator, and film batch detector, or thermoluminescent dosimeter, and proportional counter. So these are all the methods are used to measure the radioactivity. So the principle of this each and every methods are, you read it by using this slide, and application also very important. We'll move on to the next slide. So principle is very important because there are so many questions they're asking from this principle. Which of the following instruments works on the principle of ionization of gas producing electrical pulses? So option B, Hager-Muller counter. Which instrument is primarily used for measurement of high radiation dose in gamma radiation? So option B, scintillation counter. Which detector converts radiation energy into light flashes for measurement? Option C, scintillation counter. Which detector is used for gamma spectroscopy and radionuclidic purity analysis? So option B, solid state semiconductor detector. The instruments specifically used for measuring the activity of radiopharmaceutical is, so option C, dose calibrator. Which device is mainly used for personal radiation monitoring? Option C, film batch and TLD method. Which detector allows energy discrimination of alpha beta particles? So option B, proportional counter method. Which instruments can detect alpha beta gamma radiation but cannot measure energy? Option B, Hager-Muller GM counter. Hager-Muller counter or GM counter. Which of the following is not suitable quantitative measurement of radiation? So option C, Hager-Muller, that means GM counter, is not suitable for quantitative measurement of radiation. Thermoluminescent dosimeter are based on which principle? So option C, radiation induced change in crystals and film. So we'll discuss about the GM counter. GM means Hager-Muller counter. Construction and working principle we'll discuss. So component of this GM counter is, so GM tube. So that means glass cylindrical tube. This is a glass cylindrical tube. It's called GM tube. It has anode and cathode. So this center rod is act as a anode and the cylinder of the tube is act as a cathode. And the inner wall of the tube is coated with a conductive material and thin central tungsten wire that is act as a anode. And inside of this tube is filled with gas. So it is a inert gas is filled like neon, argon, and quenching is also called as quenching gas. It is containing the quenching gas is called alcohol or halogen at low pressure. So that means this tube is filled with the inert gas like argon or neon, along with that quenching gas like alcohol or halogens are filled at low pressure. And the end window, so this is called end window. It is made up of mica. It is also called as mica window. Through this window only it's emit the alpha beta radiations, and high voltage power is supplied through the battery, and pulse counter meter is connected with this Hager-Muller counter for recording and displaying purpose is connected. Next is the ionization of gas. So now is a working principle. So these are now, till now we have seen the construction. So construction you have to see about the GM tube. It containing cathode. That means the tube, the cylinder GM tube, it containing cylindrical tube, sealed tube. It's act as a cathode, and center tungsten wire. It's act as a anode, and gas is filled inside the tube along with the quenching gas. And the end shielded window is made up of mica. It's also called as mica window. Through this window only alpha beta radiations emit, and power is supplied through the voltage. This is the voltage, and it is connected to the pulse counter scaler for the recording and display. So it's a construction. So now we will see the working. So working. So first of all, we have to take the substance which containing the radioactivity. That substance will keep in front of the mica window. So if substance having ability to emit the alpha beta radiations, so that coming radiations enter into the mica window. Coming radiations alpha beta or gamma radiation enter through the mica window into the GM tube, Hager-Miller tube. It is a cylindrical tube. So next, inside the tube already ionizing gas is present. So after entering the gas inside the tube, the radiations ionize the gas. So whatever the radiations alpha beta is entering, it ionizes the radiations and forms electron and positive ions. So these electrons are accelerated and produce accelerated electron and causes secondary emission of electrons. So inside after the ionization, so it produces the electron and positive ions. Electrons and positive ions are produced, beta ions. So that electrons are converted into secondary ionization of electrons. So that electrons next the pulse generation. So large electrical impulses produce that depends upon the radiation energy. So that produced electrons are it produce the pulse. So that means is one radiations are entering, it get ionized, it emit the radiations. So that ionized radiations is producing the differences in the scalar. That means pulse counter. So each and according to the each and every radiations, each and every particles are entering, alpha, beta, gamma radiations are entering, and it get ionized, and for each ionization produce secondary electron. Due to that secondary electron formation, it produces the pulse it counting into the pulses, and it is displayed in this, and it get displayed. And finally quenching gas. So quenching gases prevent the continuous discharge and counting. So pulse counted as count per second. So for the number of, finally the readings are taken, the number of pulse per second. So here this is the working principle of the GM counter. So very simple. So once again let me summarize. So first we are keeping the radioactive substance in front of the mica window. So through this mica window, the particles emitted by this substance is entering into the GM tube. So GM tube already is containing the filled with the gases. So after entering the gases, so the particles that emitted radiations are ionizing that gas molecule. So due to the ionization of the gas molecule, it producing the positive ions and negative ions of the electrons. So this negative ions of the electron move towards the anode, and positive ions of the ionization, it move towards the cathode. So due to this movement, it produces the pulses. So that pulses are recorded per second. So this is the simple working principle. So here the electron and positive ions are produced due to ionization of gas. So this electron and positive ions are moved towards the electron move towards the anode, and positive ions move towards the cathode. So these movements are recorded as a pulses per second. That's it. So next is the scintillation counter. The scintillation counter is a sensitive instrument used for the detection and measurement of ionizing radiation, especially in nuclear medicines. and radiopharmaceutical analysis. Construction, it consists of scintillation material that emit lights. That may emit light, it's called scintillation, which is struck by ionizing radiation. And common scintillators include sodium iodide activated with thallium for alpha rays and zinc sulfides for alpha particles and plastic scintillators for beta particles. The scintillator's crystals is enclosed in a light tight housing optically coupled to a photomultiplier tube. The PM tube, photomultiplier tube, consists of photocathode and series of diodes and anodes. So high voltage of power supply is connected to the photomultiplier tube. The output is linked to a amplifier and pulse height analyzer and counting system. So here you understand simply scintillation counter, it is made up of sodium iodide activated with thallium. It's a scintillation counter, it's a well type, and this metals are made up of sodium iodide activated with thallium. So it is a type of uh, it produces the light. So that light is called, flash of light is called scintillation. Scintillation, that means emit the, these materials are emit the light. So that emitted light is called scintillation. So whenever we are keeping the uh, substance, which substance we want to measure the radioactivity, that substance we will use to keep inside the scintillation counter. The scintillation counter is connected with the photomultiplier tube, and photomultiplier tube it containing cathode and anode. So two parts are there in scintillation counter. So now is the construction. Construction is very simple. So it is a scintillation material. It is made up of sodium iodide activated with thallium, and it's connected with the PM photomultiplier tube, and photomultiplier tube is connected with the cathode and anode. So this is the construction. Now working, we will keep the part substance inside the scintillation counter. So the substance will emit the alpha beta particles. So this alpha beta particles are, it strike the wall of this scintillation counter. So scintillation counter already it's made up of sodium iodide and thallium. And when this alpha beta particles strike on the wall of this scintillation counter, it emit the radiations. It emit the flash of light. It is emit the flash of light. So that light is received by this photomultiplier tube. It's received by PMT, photomultiplier tube. So photomultiplier tube is received. When once it is received by the PMT, first is entered through the cathode. So this cathode is a it is receiving this light, it's converted into the electron. It produces the number of electrons. So that electrons move towards the anode. So these movements are recorded as the number of pulses per second. So this is the working principle in the scintillation counter. So we'll move to the questions. The main function of the Hager-Muller tube is to, option B, detect ionizing radiations by producing electrical impulses. Which gas combination is commonly used inside a Hager-Muller tube? So option C, inert gas like argon and neon, and plus quenching gas like alcohols and halogens. The thin mica window in a Hager-Muller tube allows detection of, so option C, alpha beta particles. In Hager-Muller counter, a large electrical pulses is produced due to, so option C, Townsend avalanche of electrons. Which of the following is a scintillator used for gamma radiations in scintillation counter? So option C, sodium iodide activated with thallium. Scintillation counter works on the principle of, so option C, conversion of radiation energy into light energy, then into electrical energy. This is a very important principle in scintillation counter. Radiations alpha, beta, gamma radiation when strike on the wall of the sodium thalide wall, it emits the light energy. So that radiation's energy is converted into light energy. Then this light energy converted into electrical signals. So next is a safe handling of radiopharmaceuticals. So principles of radiation protection is low as reasonably achievable. Safety measurement, minimum of time exposure, maintain maximum distance, use adequate shielding, use lead container and syringe shield, and wear dosimeter badges, avoid contact, direct contact, use forceps and tongues. And storage guidelines is very important. Store in shielded lead container and clearly labeled with name of the radionuclide, activity, date and time, separate from the non-radioactive drugs, and secure restricted access areas, and maintain inventory records, and short-lived radioisotopes stored until decay. So disposal of radiopharmaceuticals. So method: decay in storage, dilutions and release, returns to supplier, and authorized disposal facilities. So here the applications: short decay in storage, short half-life isotopes, dilutions, very low level waste, and return to supplier, shielded source, and authorized disposal, so long-lived isotopes. So it must meet regulatory clearance levels before disposal. So regulatory guidelines authority in India, Atomic Energy and Regulatory Board, and Baba Atomic Research Center. So these are abbreviation of this. International bodies are International Atomic Energy Agency, International Commission on Radiological Protection. So regulatory requirements are licensing for use and storage, and personal training, radiations monitoring, proper documentations, and emergency protocols. The principles of ALARA in radiation safety stands for option B, as low as reasonably achievable. Which of following is not recommended for storage of radiopharmaceuticals? So option D, open shelves in common laboratory. Short-lived isotopes should be stored. Option B, until they decay to safe level. In India, the regulatory authority responsible for radiation safety and control of radiopharmaceutical is option C, AE, Atomic Energy Regulatory Board. In which international body provides recommendation for radiation protection worldwide? So option C, ICRP, International Commission on Radiological Protection. So biological effect of radiations and precautions in use of radiations. So you take the screenshot of this and you read it. So because it is very important. So aspect and description and examples of the compounds, and this one's a category and precautions of this each and every category of radiations. So here is applications oriented. So genetic effect, so mutations, and so take a screenshot and read it. Which of the following is a deterministic effect of radiation? Option C, skin burns. Which tissue is considered most sensitive to radiation? Option C, bone marrow. Which of the following is a precaution to minimize exposure to radiation? So option C, maximize distance from the source. So next is application of radiations. So the important compounds, sodium iodide. Sodium iodide is used for the thyroid diagnosis and therapy. Technetium 99 is used for diagnostic imaging, and cobalt 60 cancer radiotherapy. Phosphorus 32 leukemia and polycythemia. Ferric citrate Iron 59 is used for iron metabolism studies, and barium sulfate is a X-ray opaque medium, radio opaque medium. It is used for GIT, gastrointestinal tract imaging. Which radioisotope is commonly used for thyroid diagnosis and therapy? Option C, sodium iodide and iodine 131. Technetium 99 is primarily used for, option C, diagnostic imaging. Which of the following is a gamma emitting isotopes used in cancer radiotherapy? So option C, cobalt 60. Phosphorus 32 is mainly used for, so option C, leukemia and polycythemia treatment. Iron 59 is used for, option D, iron metabolism studies. Which isotopes emit both beta and gamma radiation? So option B, iodine 131. Which isotopes could be chosen for hematological studies like red blood cells turnover? So option B, iron 59. Which of the following is not a radiopharmaceutical but is used as an X-ray opaque medium? So option B, barium sulfate. It is also called as barium meal. Barium meal. For gastrointestinal imaging, the preferred contrast medium is, so option D, barium sulfate or barium sulfate meal. The preferred radioisotopes for non-invasive cardiac, renal, bone imaging is, so answer in the comment box. So all of you join in our WhatsApp community. You will get hands-out material. Thank you. Like, subscribe and share.